A Boeing 787-9 begins its takeoff roll. It is accelerating at an abnormally slow, labored rate. Ominous gray smoke is trailing from the undercarriage. The cockpit crew calls out V1.
We now have footage from inside the plane during the takeoff roll of this 787-9 that had an overrun and a tail strike yesterday. The video shows us what we already knew, that the plane overran, but now we can hear it hit lights on the runway threshold and hear when it makes contact with dirt off the paved surface.
As the end of the runway approaches, the first officer calls for a stronger rotation, a desperate attempt to force the aircraft into the sky. The plane overruns the paved surface. As the nose finally lifts, the tail slams into the dirt and shatters the glowing threshold lights at the very edge of the airfield. Forcing this late rotation saved the flight from a high-speed ground collision. However, the airstrike created an overrun for a new, unpredictable crisis. Once airborne, the focus shifts to a thermal crisis mounted inside the wheelbase. The energy generated during that labored takeoff is now trapped within the airfield. Inside the cabin, the landing gear display quivers and hums as brake calipers monitor the brakes do not normally heat up during climb. This reading indicates a massive mechanical failure, actively threatening the gear's structural integrity. Recognizing the severity of the thermal spike, the captain declares an emergency. The crew requests an immediate return to the airport, knowing they have a very limited time to act. Escaping the ground only bought the crew a small window. They are now flying a ticking thermal bomb, with invisible heat levels rising just inches away from high-pressure fuel and hydraulic lines. To find the cause of the sluggish takeoff, we must look into the mechanical anatomy of the 787's wheel well, specifically the electric brake actuator. Normally, actuators retract, creating a clear gap between brake pistons and carbon rotors. On Flight 34, a single actuator failed to retract. Approaching 200 miles per hour, these carbon pads ground against the rotors, generating immense continuous friction. This millimeter-scale mechanical hangup acted as an invisible anchor, overpowering the thrust of the jet engines, nearly causing a fatal crash. This friction transformed kinetic energy into heat, erupting in sparks and flames. Carbon brakes absorb heat during landing, but trapping this superheated energy inside the wheel well during takeoff rapidly weakens the surrounding hydraulics and tires. This trapped inferno is exactly what triggered the 9.9 alarm in the cockpit, alerting the pilots that their landing gear was becoming a liability. While the 787 is aerodynamically stable in flight, the superheated carbon assembly has become a loaded weapon, threatening the tires. Air traffic control clears the flight for a holding pattern. The crew begins a calculated orbit to burn off thousands of pounds of heavy fuel.
It will take about 45 minutes to do the changes of the fuel. And then we come back and landing, normal landing. So we thank you for your
inspection of the smoking undercarriage. ATC confirms the visual damage. With this information, the crew prioritizes a highly controlled landing, knowing they must minimize the impact stress on the left main gear. This 45-minute hold was a vital safety process. By shedding weight and verifying the damage, the pilots increase their chances of a survivable landing. The crew enters a strict challenge and response flow to complete the emergency landing checklist. Every action is cross-checked as they turn onto their final approach. The gear is extended, showing 3 green lights. Despite the long hold, the brake temperature remains dangerously high at 9.49. As the 787 touches down, it transfers weight onto the superheated left gear. The thermal stress peaks, sequentially exploding the tires and shredding the rubber. The combination of the landing impact and the extreme trapped heat is more than the structural casing can handle. The tires fail instantly. As the tires blow out, the aircraft yaws violently toward the edge of the runway. The crew deploys full spoilers and reverse thrust, fighting the asymmetric drag to keep the jet on the center line. The mechanical failure dictated that the gear would be destroyed, but the pilot's rapid, coordinated response dictated that the aircraft would stay on the runway. The 787 comes to a complete stop on the tarmac. Emergency fire crews immediately swarm the aircraft to douse the smoking remains of the left gear. Despite the severe trauma to its undercarriage, the aircraft is safely parked. the integrity of the fuselage and safety of everyone on board remained intact. This recovery was a direct result of crew resource management. By dividing the labor, one pilot flying while the other managed the failing systems and tower communications, the crew prevented a chaotic failure from becoming an unrecoverable disaster. A single unreleased
And everything is set now. So
phase of flight. Complex machines will always have microscopic points of failure. Safety is maintained not by the absence of faults, but by the human adherence to checklists and communication that breaks the chain reaction of disaster. A failure of millimeters was met with a response of miles.